Welcome to Calculus 1. In this lecture, we will be talking about the real number system. Numbers are the terrain for calculus. So how exactly do we define numbers? Well, before we get into that, let's talk a little bit about the game of chess. More specifically, what is a pawn? Well, in effect, a pawn is defined by the rules that the pawn must follow. For example, a pawn can only move up one space at a time, and when capturing another piece, it can only capture diagonally. In essence, we define numbers the same way we define the pieces of a chess game. We define numbers implicitly by specifying the rules or axioms that they must obey. Now, there are three types of axioms. There are 9 field axioms, 4 order axioms, and the completeness axiom. Before we talk about what these axioms are, let's first talk a little bit about quantifiers and sets of numbers. Terms such as for all and there exists are often abbreviated with symbols. For example, this upside down A means for all, this backwards E means there exists, and this symbol means in. Furthermore, there are sets of numbers that are so prevalent in mathematics that we give them special symbols. This N is the symbol for the natural numbers, which are 0, 1, 2, 3, and so on. Note that some textbooks start the natural numbers at 1 instead of 0. The integers, denoted by this Z symbol, are the natural numbers and their negative counterparts. Next, we have the rational numbers. The rational numbers are denoted by the letter Q. The rational numbers are the set of numbers A and B in the integers, B not being 0, such that A is divided by B. In other words, rational numbers can be denoted by fractions, such that the numerator and denominator of the fraction are integers, and the denominator is not 0. And then we have the real numbers, which is denoted by the letter R. The real numbers are what we are working on defining right now. Now let's get into what these axioms are. We'll start with the 9 field axioms. So first, there exist operations addition and multiplication on the real numbers such that the following. Note that we don't define explicitly the operations of subtraction and division. Those are implicitly defined by the axioms. Our basic operations are addition and multiplication. So first, we have associativity of addition, which states that for all A, B, and C in the real numbers, bracket A plus B, close bracket, plus C is equal to A plus bracket B plus C bracket. And this essentially means it doesn't matter how we add the numbers, you'll always get the same result. We have commutativity of addition, which states that for all A, B, and R, A plus B is equal to B plus A. In other words, it doesn't matter which order you add numbers, you'll get the same result. Next, we have the additive identity, which states that there exists a 0 in the real numbers, such that for all A in the real numbers, 0 plus A is equal to A. In other words, if you add 0 to any number, you'll just get that number back. And then we have the additive inverses. For all A in the real numbers, there exists a negative A in the real numbers, such that A plus negative A is equal to 0. We also have associativity of multiplication. So for all A, B, C in the real numbers, A times B times C is equal to A times B times C. That is, it doesn't matter how you multiply numbers together, you'll always get the same result. We also have commutativity of multiplication. So for all A, B in the real numbers, A times B is equal to B times A. That is, it doesn't matter what order you multiply the numbers, you'll always get the same result. We also have the multiplicative identity. So there exists a 1 in the real numbers, such that 1 is not 0, that is, the multiplicative identity is different from the additive identity, and for all A in the real numbers, 1 times A is equal to A. So in other words, If you multiply any number by 1, you'll get that number back. We also have multiplicative inverses. So for all a in the real numbers, a is not equal to 0. There exists an a inverse such that a times a inverse is equal to 1. Finally, we have the distributive property. For all a, b, c in the real numbers, a times b plus c is equal to a times b plus a times c. Let's now move on to the order axioms. For all a, b, and c in the real numbers, there is a relation less than on the real numbers satisfying the following. First, we have the trichotomy law, which states that if a is not equal to b, then either a is less than b or b is less than a, but not both. We have the transitivity law, which states that if a is less than b and b is less than c, then a is less than c. Further, if a is less than b, then a plus c is less than b plus c. And finally, if a is less than b and 0 is less than c, then a times c is less than b times c. Now that we have some fundamental axioms under our belt, let's look towards a theorem and how we can prove it. In this theorem, it states that for all a and b in the real numbers, if 0 is less than a and b, then 0 is less than a plus b. Further, if a and b are less than 0, then a plus b will also be less than 0. Here's the proof for this theorem. First, let's start with our givens. We're given that a and b are a part of the real numbers, and 0 is less than b, and 0 is less than a. So let's start with 0 is less than a. We can add b to both sides of the inequality, and we will get that 0 plus b is less than a plus b, and we can cite axiom 12. But since 0 plus b is equal to b, citing axiom 3, the additive identity, we have that b is less than a plus b. But since 0 is less than b, and b is less than a plus b, by the transitivity property, we can say that 0 is less than a plus b, and we'll cite axiom 11. And that black square in the corner symbolizes that we have finished our proof. As an exercise to the viewer, I encourage you to try to prove the second part of this theorem. That is, if a and b are less than 0, prove that a plus b is also less than 0. The format of the proof is very similar to the one that I've shown you here. So now let's talk about the types of numbers we have. Currently, we're trying to construct the real numbers. And so far, we have the natural numbers. We also have the integers. And we also have the rational numbers. However, there's another set of numbers that we haven't discussed so far. Those are the irrational numbers. Now, there are two types of irrational numbers: algebraic irrational numbers, like the square root of 2, and transcendental irrational numbers, like pi. You can refer back to the axioms that we have discussed so far and see that these numbers are not included in the axioms that we have discussed so far. So what do we do about constructing the irrational numbers? Just to send the point home a little bit, let's talk about roots of polynomials. Consider the following equations. We have x squared minus 2 is equal to 0. We have x cubed minus 2 is equal to 0. And finally, we have 31 x to the 5th minus 7/3 x to the 3 plus x squared minus 17 is equal to 0. Now there are numbers x such that when you put them into the equations, it will give you 0, and these numbers are called roots of the equation. However, these roots are likely not rational numbers. You can look at x squared minus 2, and if you put in the square root of 2, you'll get 0. However, the square root of 2 is not a rational number. So what should we do about the roots to most polynomial equations? currently our axioms don't allow us to construct these numbers. So is it simply that we cannot construct these numbers and we cannot solve these equations? Well, that seems rather unsatisfying. We could impose new axioms for every irrational number, like we did for the additive and multiplicative identity. We simply created axioms such that there are numbers 1 and 0. We could create a square root 2 axiom and state that there is a number such that it is called square root of 2, and when put into the equation, x squared minus 2 gives 0. However, doing that for every single irrational number is, well, rather irrational. So before we deal with the irrational numbers, let me take a quick detour into least upper bounds, also referred to as supremums. An upper bound of a set is a number that is greater than or equal to every number in the set. For example, let's consider this set, which contains the numbers 3, 7 over 3, 52, and 511. Now, what is an upper bound of this set? Well, for example, 5007 is an upper bound because 5007 is greater than 3, it's greater than 7/3, it's greater than 52, and it's also greater than 511. Now note that our definition states greater than or equal to. So 511 is also an upper bound to this set, because 511 is greater than or equal to 3, greater than or equal to 7/3, greater than or equal to 52, and also greater than or equal to 511. In fact, it's equal to 511. Now, if a set has an upper bound, we say that it is bounded above. Further, the least upper bound of the set is the smallest of the upper bounds. So in this case, the least upper bound is 511. We can now talk about our final axiom, the completeness of the reals axiom. It states that every non-empty set of real numbers that is bounded from above has a least upper bound that is a real number. Let's consider the following set. The set S, where x is an element of the rational numbers, so all the numbers we have constructed thus far, such that x squared is less than 2. For example, x can be negative 1.4 because negative 1.4 squared is 1.96, and 1.96 is less than 2, so x squared is less than 2, so this number is in the set. X can also be 1 because 1 squared is 1, and 1 is less than 2, so 1 is also in the set. So essentially, all numbers such that when squared are less than 2 will be in this set, and those numbers must be rational numbers. Moving on, this set is also bounded from above because it has an upper bound. For example, 5 is an upper bound of the set because 5 squared is 25, and 25 is greater than 2. So let's ask ourselves, what is the least upper bound of this set? Well, we would like to say the least upper bound of the set is the square root of 2, because the square root of 2 is greater than or equal to all the numbers in this set. And in fact, the least upper bound is the square root of 2. The reason for this is that the completeness of the reals axiom guarantees that this set has a least upper bound, and it in effect generates the number square root of 2. It's okay if this doesn't make sense to you right now. It takes some time to understand what this is saying. However, if you take some time to think about it, you'll eventually be able to understand the completeness of the reals axiom. Finally, a note on infinity and dividing by 0. First, let's talk about whether or not infinity is a number. Well, if we define infinity like this, 1 plus infinity is equal to infinity, and 2 plus infinity is equal to infinity, then the following is true. 1 plus infinity is equal to 2 plus infinity. If we add the additive inverse to both sides of this equation, we get 1 is equal to 2. Now this is obviously not true. Therefore, there are logical problems that occur when we allow infinity to be a number. So therefore, we exclude it in the real numbers. Now what about dividing by 0? Well, suppose the following. A times the multiplicative inverse of 0 is equal to b. in essence, a divided by 0 is equal to b. Well, if this is true, then we can multiply both sides by 0 and get a is equal to b times 0. However, b times 0 is equal to 0. So therefore, division by 0 cannot be permitted because it will lead to a contradiction.